turn on the. All right. Hello, everyone. Welcome to join this semester's ROAR seminar. So this is our first seminar for this semester. And then I have been asked by CK and Chris to organize a very interesting talk to talk about some great experiences of the Indy Autonomous Challenge. And as many Berkeley students know that we also have very passionate group at Berkeley doing autonomous driving, artificial intelligence, and computer vision. But I think that in the Indy Autonomous Challenge is very unique in the sense that it is a great combination of the industrial and the university effort and really bring the people of a very diverse background together. And I think that in that aspect, it is very unique. And then some of our students have already participated as part of the team to attend the 2021 to 2022 season organized by Indy, the Indy racing. And then it's my pleasure today to invite one of the teams that involve Berkeley students and also two other teams. One is from the University of Hawaii, another one is from the UCSD, to give us a overview and then to present some of the what they have learned and also the challenges, so that we can look forward to discuss also how to build a greater solution for the future challenges. And I think that's a great opportunity for many of our Berkeley students and also affiliated programs in the Bay Area, including high school students. We actually send out the invites for some of our affiliated high school program students to also join the meeting today. And today's meeting seminar is recorded. Just for your information, if you don't want to have your face to be recorded, you can feel free to turn off your camera, but we always welcome your participation. You can either use your microphone or you can type in your questions in the chat. So next, I'm going to hand it over to the three lead person to organize today's presentation part of the seminar, Chris, CK, and Gary. And in particular, Gary is the team principal of the AVT program. He lead the effort to compete in the 2021 and 2022 season of the Indy Autonomous Challenge. And then he is also the principal investigator at the University of Hawaii Autonomous Vehicle Team. So Chris, CK, and Gary, I'm going to hand it over to you.
Thank you so much, Alan. Thanks for that intro too. I think you saved me the trouble here. So let's go ahead and dive right in. So the Indy Autonomous Challenge is a $1.5 million prize international competition among university teams to program a Dallara AV-21 race car. So in this photo here, we can see the 9 teams that competed this race season, all kind of standing behind their cars. If you look for the orange shirts, as you can see us wearing here, in the back on the left, you can spot the Hawaii team. So what we're going to do is we're going to open up with a promotional reel. There was a Netflix documentary film crew that's currently following the IAC race seasons. The video that you're about to watch was made from the October Indy footage as a teaser trailer for CES, which happened in January of this year. So if you have trouble streaming or experiencing any video lag, there's a shared link in the chat if you'd like to follow along with this video. But Chris, you can go ahead and move to the next slide and take us out.
Today is the day that has been 2 years in the making.
Race day, October 23rd, big day at IMS.
Today is the day, and winner takes $1 million.
We're willing to push and see what that car can do.
I still can't believe that I am the team lead for one of the handful of autonomous racing teams in the world. Once the car leaves the pits, it will make decisions based on the data it sees on the track. We could be sitting in the pit smoking cigars all we want, and the car will do its performance laps, warm-up laps, come home, stop in front of my pits.
Start your software and crank your engines.
Go, baby, go.
She's out.
Ready to go.
Car floor is in motion.
Baseline switch.
Okay, speed heading, please.
We lost connection. We obviously hit a failure mode that we weren't expecting.
Part of engineering and a part of like pushing forward is realizing that there's going to be mistakes made along the way.
Two-lap average for the German team, coming in at 135.944 miles per hour. That is a new record.
I have your $1 million check.
You can only go faster from here, so I'll see you at the next race.
We have to get to the next level and the next level. Multiple cars on the track at these kinds of speeds, navigating each other. It's going to start with CES in January.
For Vegas.
For Vegas.
Woo!
Our mind is already on Vegas. We plan to be really fighting for that win.
We are proving the limits of AI, the limits of autonomous systems. This is the grand challenge, the next frontier for self-driving cars.
Thank you, Chris. So we can skip on over to the next one. So today we're meeting with Team 7, the AI tech racing team. We can move on to the next one here. So we have a photo post the IAC competition at CES, the one that this promo reel was for. This team photo is missing quite a few essential team members. There were an incredible number of contributors who made this race possible. I'll point out the speakers with us today here in this photo. From the Berkeley Perception team, Zihao Deng, also known to his friends as Cake, is featured right kind of in the center middle there. I don't know if Chris can point it in there. Chris Batista is featured on the right. You can kind of see him towards the front of that race car. And then myself in the middle doing a little bit of this here. And then on the left is our team principal, founder, and fearless leader, Gary Passon, all the way on the far left over there. If everyone can take a second to find their Zoom applause emojis, I think we should give Gary a round of applause for taking the time to be here with us today. Thank you so much, Gary. So we can flip on to the next slide here. This is just a short overview of what we're going to cover today. We're going to take you through the timeline of how the AI racing tech team brought together this incredible and hardworking group of students and collaborators and ended up as one of the 9 select global teams this IAC season. To take us through the origin story of AI racing tech and to talk about why the Indy Autonomous is a truly unprecedented university opportunity, I will give the floor to Gary Passon.
Thanks, CK, and let's go to the next slide. So in the beginning, a small group of us in Hawaii took a look at what we had in terms of the autonomous program, STEM, with the local high schools, and where we were headed as a school, and decided to embark on a program of autonomous vehicle technology, as well as a parallel program in autonomous on-water technology. So this represents the rover or ground-based side of that strategic initiative, and it was it started out as a class that I was asked to teach at the Maui campus in the spring of 2020, and was you know, an excellent opportunity to kind of see what it is we were doing and what it is we could do and what it is that we might want to do. And as part of that, very quickly, the program at UH expanded beyond jet racers, expanded beyond 10th scale vehicles, expanded to 5th scale vehicles, and ultimately started to expand to a autonomous racing go-kart program. So the very quick evolution of the program there. And because of the success that the team had had in preparing for the autonomous EV challenge for go-karts, it was recognized as one of the inviting schools to participate in the IAC if it applied. So we did our application. And we were excited about being recognized as one of the teams to compete, and then embarked on a simulation competition, which consisted of multiple rounds of developing autonomous racing vehicle software, but executing it only in the simulator. And the idea of that simulation challenge was much like the DARPA challenges or some of the other university level challenges that have gone on over the last few years. It was to reduce the cost of entry and prove out which teams had the had the commitment, had the chops, had the desire to really participate in a program like this. And so out of the 41 universities that began this journey, at the end was 9 teams that were going to be selected. And in some cases, universities partnered up with other universities, and research centers partnered up with other research centers. And really the top 9 of the competition teams were then selected and given the opportunity to modify and develop software for the vehicles that we're going to talk about here in the rest of today. So as University of Hawaii went through that, and we finished 6th in the simulation challenge, and began to prepare for Indianapolis, we began to realize that this was an opportunity that was honestly bigger than us, and I think also was an opportunity for us to reach out and collaborate with other schools. So our initial collaboration was with UC San Diego. And that's because we were jointly collaborating on the autonomous EV kart program. So we were already partners. We were already very used to working with each other. We were already having dialogues of how to divide up this very significant opportunity and challenge. And so we, in 2021, we invited them to join us as a partner team for, for ART, AI Racing Tech. And they came in and did an amazing job. And in parallel to that, Chris, who's going to be talking later through this, who was originally part of the program when it was a UH program, moved to Berkeley and extended his interest in participating. And he and I talked about maybe there's some folks up at Berkeley that we could begin to introduce this program to, and maybe there's some interest there that they may have, and we could meld their skills, knowledge, and commitments in with ours in the University of California, San Diego's. So Chris did an amazing job of that. A couple of those folks are here today, and they participated in the program as we moved forward through 21. And then and that culminated in, and again, we're going to talk about this in more detail later on, culminated in an IAC second round, which was at the CES show, in which the speeds and the performance of the vehicles were substantially moved up a notch, both in terms of complexity, but also in terms of developing greater safety and technology standards. So Berkeley and University of California, San Diego and Hawaii all went to Las Vegas. We spent about a little less than a month there, but roughly a month with a few days off for Christmas. And that was our second event. And we came back from there, I think, smarter, wiser, and very committed to continuing this program. So where are we today? We're moving forward in the this year in 22 to compete not only in the EV Grand Prix race at Indianapolis in May, which I think will give us an opportunity to expand and test the next generation of our autonomous vehicle stack, but also prepare us for a race in late summer to early fall that's going to be scheduled for the full-scale Indy Autonomous Challenge AV-21. So we're still working. There's plenty of opportunity for individuals and schools to join us, and we're very happy to be here today to give you guys some information about the program, and hopefully have some of you. We would like to invite you and have some of you join us on this journey. So one of the things that really made a big difference to us was in evaluating what we were going to work on is what kind of programs are we going to engage ourselves in, and what makes this program different? I mean, why this versus a number of different autonomous challenges that are out there? First of all, it's bigger and more well-known. So there's been millions of dollars of earned advertising value, articles in every major tech magazine, articles, TV coverage for this particular show, local coverage for the different schools that have participated. And all of that has done is bring greater and greater appreciation for the challenges that we're trying to do. It also is different in that the continuing and evolving requirements. So rather than saying, here, do this thing, every time we do something, the next time we look up, they've raised the bar, they've moved the goalposts, they've forced us to get out of our comfort and develop stuff that really hasn't been developed to the degree and to the extent that the IAC teams have been challenged to do. Wheel-to-wheel racing in million-dollar race cars is just something that a year or two ago people would have said, great idea, 5 years out. And now we're already beginning to see the fruits of that labor. Another thing that makes this different is industry participation. An awful lot of university challenges prohibit industry from being involved to any degree. This particular challenge invites industry in, and the reason for that, and we were one of the folks that lobbied for that, is that so much of what the students need to do when they leave their university training is integrate into industry. And the sooner that they can get a flavor of that, a taste of that, start to handle themselves or their projects in a way that's going to align itself with the way industry does things, the better off that student's going to be. So that helped bring great opportunity to the students, and it also helped bring in financing because it's expensive to run these programs. And then the next one is New Frontiers. So autonomous, they've been, I mean, I'm sure everybody here knows there's been autonomous vehicles driving around for 10, 15 years now, but none of them have been operated at anywhere near the kind of speeds that we're asking these vehicles be tested at. So just as an example, just the delay that occurs in a rotating lidar at 200 miles an hour is 25 feet of movement. So you have to de-skew the data in a way that just isn't necessary in a traditional autonomous vehicle challenge. So so we had to discover those things, figure those things out, develop methods and algorithms to address those kinds of things. Next slide. And there's a lot another thing that just has made this program, I think, atypical, is that from a broad spectrum perspective, we have to look at everything from AI to safety engineering. We have to look at everything from vehicle dynamics to high-level mathematic optimization systems to be able to find solutions that we need for our challenges. We have to understand organization. These are multi-school, multi-year, multi-discipline challenges. And so you have to understand how to organize that. You have to understand how to develop timelines for that. You have to be able to manage feature assessment. What do we need to do, and not do things that you don't need to do? We need to prioritize. We need to understand the practicality of different features or different approaches, because we have a finite period of time. We have a finite computer in terms of memory and processing. We have a finite set of sensors, and we have to make those work, and not in theory, but in reality. So that's a really big thing for us. Doing the cross-university, cross-team was critical to us. We felt that was important for our students to learn and work together across time and distance boundaries. At the same time, we wanted to focus ourselves on open source, open dev, software reuse. We think those are the directions that industry's moving, and we think that that's very clear. And so we wanted to get the most experience we could for the students in those particular areas. And then last, this is just an amazing resume maker. A lot of students participate in a number of different challenges, but this is the biggest challenge right now. And so to have that on your resume, to say one was a participant in that and a contributor to that, I think is really going to help the students move forward in their job searches. And we've already had job offers and then we'll talk a little bit about that later on. Next slide. So I'm going to turn this back to CK and talk a little bit about what's next.
Thanks, Gary. That was great. Okay, so let's talk about training and hands-on experience. How were the students involved able to gain the skills to be competitive at IIC? The UH and UCSD students came up through similar pipelines. They all started with the autonomous 1/10 cars through Gary and Jack's programs, much like our ROAR program here, and they moved to larger and larger scales, finally ending at IIC. So the upcoming project timeline for the UH and UCSD partnership involves working with the same IIC software stack, first for the EV Grand Prix that's coming up this May, and then which is a national autonomous go-kart competition that's hosted in West Lafayette, Indiana. For Berkeley students thinking about getting involved, the first stage of the pipeline to onboard and train students really starts here. You can switch to the next slide. So about the EV Grand Prix. The EV Grand Prix is, like I said, an international competitive electric go-kart competition that gathers universities together to compete with fully autonomous race cars. So the software stack from IIC is fully adaptable to the EV Grand Prix. Our goal is to make modular, reusable software that we can extend across multiple projects. So what students learn in one competition can be translated to the next. So to tackle the challenges of the race season, there are multiple software and hardware focused teams that span across both of the universities. To speak more on these dev teams on the October race season, where future students are needed, I'm going to hand this over to the member of AI Racing Tech who has been involved for the past 2 years, well before his Berkeley days, the catalyst for the Berkeley students' involvement, Perception Team Lead, Chris Batista.
Good, thank you, CK. Don't remind me of the days I lived in Hawaii. I'll make it back one day. Sounds good. Well, it's exciting to meet everyone. I hope we have a few future team members here. I'm excited to tell you about the parts that go into making this incredible challenge possible. As you can imagine, an autonomous car has dozens and dozens of different subsystems. And as Gary mentioned, we had to gain some experience with handling all of them. The first thing that we thought about was control. You can imagine any control problem that is happening on a lab robot moving at a few miles an hour is just going to be compressed into incredibly small time scales and incredibly fast speeds as you get up to speed with a race car. And that translates over into localization too, as we're Kalman filtering, you know, some of you might be familiar with that from your coursework or something like that, as we're trying to figure out where the car is in a few seconds, we could be hundreds of meters away. And so how do we account for that? How do we build algorithms that if our sensors blip out for a couple of seconds and we're down the track, we can recover from that? And then finally here, we've got the team that the three of us students here worked on perception. This is sort of the eyes and ears of the car, primarily using a set of lidar units to see the other cars, eventually to see the walls, and to understand what obstacles need to be avoided on the track. There were a few other teams of equal importance as well. I want to highlight navigation team here. This is what perception was mostly working with and gearing towards. Once you found, and here you can see in the back point clouds as the car drives down the track. Once you've found some of those obstacles, where do those go? They go to the navigation team, which is doing path planning and obstacle avoidance to try to keep the car moving as fast as possible without crashing into anything. And there's a few more as well. Some of these questions depend on the geography and the vehicle dynamics, and those two things weave together as you figure out, for this particular car on this particular track, what's the best route that maximizes the speed that the control strategy can achieve. That's the vehicle dynamics team. And then the track operations and logistics, that might be the most fun. That's mission control, where we've got walkie-talkie crew firing up the car, ensuring safety on the track, clear the pits, and making sure that this incredible machine can keep running from a hardware perspective. All right, I was asked to tell a little bit, and Gary already covered the Indy 500 story a bit, so I won't go into too much detail, but essentially we brought everyone together in Indiana. We had an amazing kickoff where we attended the Indy 500. We brought everyone together for a few days, and then we got to work. So we were working in C++, Python. We learned a ton of DevOps. As Gary mentioned, really relevant industry technologies. And we were fortunate to be mentored by some incredible industry personnel who you can see on the right side here. A couple of folks from our sponsor, Gaia. I don't know if you can't tell, Gaia was sponsoring us for the car wrap. And so they graciously provided two of their engineers who were in the conference room with us at midnight eating pizza, trying to figure out how to make these algorithms work. We owe a lot of help and a lot of learning to these guys. So we learned a lot of things. We learned integration engineering, pulling together, a bunch of different pieces of hardware from different manufacturers and making them work together. We learned development operations, which is something that's often overlooked in school, but super important to having a distributed and large team work together efficiently. We learned a lot about algorithms. I mean, Jahao is going to get in later to the tracker that he developed, but some of these things that we implemented were graduate school level, theses type algorithms that we were reading a paper and turning into code. So it was an exciting time. We competed on the 23rd. We achieved our highest speed ever. Gary, you can chime in here. I think we got to, was it 87 miles an hour? And it was just a tremendous rush. The event was being televised. We were cheering on the other teams. A car would hit the highest speed and then another car would beat it by 2 miles an hour. There were some code bugs that caused heartbreak when cars would come into the pit too early. A few crashes that just, we felt for the teams. And overall, it was just sort of a once in a lifetime experience, really, to be there on race day. Speaking of the other teams, I won't go too much in depth on this slide, but we're competing against some of the best and honestly collaborating with some of the best, from Auburn to MIT to the Korea Advanced Institute of Science and Technology. It really felt more like a collaboration among dozens of leading world schools working together on these cars. We would share data. In some cases, we would share code or drivers. And it was really awesome to be able to collaborate with people across the world in this context. Yep, here we are again on the podium after the race. Gary was sick, so he's featured there on the iPad. And so we wanted to do it for Gary, and it was a tremendous rush as we pulled everything together and got out there on the racetrack. So we're grateful for Gary's mentorship and presence throughout the race, even when it's on an iPad. I'm going to hand it back actually to Gary to talk about the hardware. I know for many students, this is one of the most exciting parts of the challenge.
All right. Thank you, Chris. And by the way, thank you for all the amazing things you've done for the team over the last year and a half, and the contributions that you've made, and the many, many, many long hours that you and all the other team members put into to get us to where we are. This is another thing that makes this competition very different. The Dallara AV-21 is actually a modified version of an IL-19, which is a Dallara platform that's used for Indy Lights racing. So this is not a lightweight, put together in a hurry race car. This is a very serious $1 million plus piece of hardware before we start doing anything on the autonomous platform. So it's supported by, when the teams are together, it's supported by professional race mechanics and engineers who make sure that when we get ready to go out with our autonomous package for testing or for qualifying or for the race, that the cars are ready. Bridgestone provided specific racing tires, of which we might get 5, 6, 7, 10 laps on, lock up the brakes, and they get thrown away. A broad range of industry contributors are all over that this particular vehicle, all having contributed time, money, and talent to the success of this particular program. So in this car is an autonomous spec package. And by what does that mean? What that means is that specified by rules is and you can kind of see it sticking out without the cover on it. By rules, the specific sensor package, computing package, controls package, hardware is all specified. And then it's pretty much every man for himself. But as Chris mentioned, the quality of the teams in the universities that were participating, it was never a us versus them. There was always a high degree of interaction. Gosh, I'm having a little trouble with this. Oh yeah, did you try that? Interaction between the different teams. The hardware for this particular vehicle, as outlined here on this slide, represents state-of-the-art everything. So the Luminar Hydras are the same kind of luminars that are being specified for the high-end Mercedes-Benz cars, high-end Volvo cars. It's state-of-the-art in terms of its speed, the number of lines of processing it's doing. So each of the luminars, and you can see two of them here in this picture kind of pointed backwards, and one of them relatively low at the front, pointed forward. Each represents a little over 120 degrees of lidar coverage. So unlike a rotating lidar, these lidars cover a horizontal width of 120 degrees. On top of that, because location, just like in real estate, is critical in autonomous vehicles, we had 2 Novatel GPS systems. If you look on both side pods, you'll see GPS antennas. If you look at the front of the nose area and at the top of the roll bar, you'll see 2 more antennas. And those sets of antennas and Novatel GPSs are designed for high speed and providing the heading location even in a stop position. So these are the state-of-the-art GPS systems. They cost as much as some cars cost. And on top of that, it's a little hard to see, but the kind of little red dots next to the front lidar is cameras. And so there are 6 cameras, 2 facing forward, which gave us a degree of stereo vision to the extent we could use it, and 4 around the periphery that gave us camera visioning to support our lidars. And then lastly, on the sides, you'll see the little square boxes, and up on the top in front of the 2 lidars, you'll see another one is the radar units. So basically everything that's on anything that's autonomous vehicle wise is on this vehicle. So we would have the tools and the opportunity to not only get experience with all that, but to determine what was the best combination of sensor packages that we could do. And that was all supported by state-of-the-art NVIDIA GPUs, processing computers, and all sorts of additional safety support systems, race control. I mean, how do you, there's no driver, so you can't wave a flag, right? So you have to have communication systems, bi-directional communication systems between the autonomous vehicle moving at 160, 70 miles an hour and race control. So the race control can clearly communicate to the vehicle what it needs to do in terms of its activities on the track. So moving to the next slide. And supporting all that was the autonomous vehicle stack. And as CK mentioned, our intent from day one was always to develop that stack in a modular way and in a manner that allowed us to share as much of it possible from all of our different autonomous vehicles, from small to large. In particular, the EV card and the IAC shares a huge amount of similarities in both the camera and the lidar areas. And we did that as much as possible based on open source. Ubuntu, ROS2, as I'm sure everybody's very familiar with, Cyclone DDS, and open DDS structure. Autoware.auto and Autoware.ai are kind of the BAT, Carla, and a couple of other software bases are some of the most open and available autonomous vehicle software packages. And then back to the collaboration comments, the IAC teams got together and realized that there was still an awful lot of software to run these that really wasn't going to discriminate on who was doing the best autonomous vehicle stack. So we all contributed to a base software stack that gave the vehicles the general capabilities of at least moving, reporting itself back in, handling safety issues and that kind of stuff, so that no team had to do all of that work. We all spent a few months jointly developing that particular stack. And then on top of that was the fine work of the UH folks, the UCSD folks, and the Berkeley folks to evolve that stack and to give us a competitive software program for running in the competition. So next slide. And then I think as probably everybody here knows, autonomous vehicles need testing. And of course, it's as hard as it is to take an autonomous car out on the street, it's even more challenging to get miles for an autonomous race vehicle. So simulation becomes critical. And as part of that, developing a hardware in the loop capability to be able to handle the vehicle dynamics at the most realistic level you can becomes critical. So we're moving in that direction. As the speeds have come up, we've begun to develop that capacity above just regular simulation. We started out with ANSYS VR Experience, which is a very nice simulation package. Not very graphically, very interesting, but did give us the tools to be able to run the simulation competition. And then for Indianapolis and for Las Vegas, we moved to LGSVL, which is an open source simulation package, which regretfully is going to be ending the open source, or actually keeping the open source, but ending the corporate support for that. So that's been our go-to simulation package up to now. And we're looking at what work we could do to maintain that package and keep that as a viable alternative, or take a look at Carla and as a potential simulator. As most people, if I think probably some of you folks have played around with Carla or are familiar with it, it's a very good package for street vehicles, but misses a lot of the vehicle dynamics and the kind of sensor emulation and simulation that we need. So there's going to be some work. There's going to be some work in either of these two areas for us to continue having a viable simulation package. But that's core to the long-term success of the program. So next slide. And so that's kind of a summary of the hardware, software, and simulation. I'm going to turn the presentation back to CK.
Thank you, Gary. Gary will also be available for follow-up questions afterwards. So our next stop on the race timeline after the Indy Autonomous Challenge is the race we're headlining at CES. And for those of you who may be unfamiliar, CES is one of the most influential tech events in the world. It's the proving ground for a lot of breakthrough technologies and global innovators. So a lot of giant companies will reveal new projects there. This is our team photo here at CES. So the first and most important thing to note between IAC in October and IAC at CES is that the rules changed. You can flip to the next slide here. So while the Indy Autonomous was autonomous laps and a speed trial with one car on the track at a time, the fastest car takes it all. At CES, the game totally changed. Two cars would lap each other each round with one attacker attempting to pass and one defender until a pass could not be made and a winner was declared. So faster and faster each round. This change meant redeveloping the code base in 2 months. So from October 24th to January 7th was intense. I wish I had a photo of kind of the war room to better paint a picture of the intensity and the level of teamwork. In the Las Vegas hotel, there was this double suite just filled with monitors where they took out all of the furniture that was called the war room. So many of the members of the team put in 14-hour days over Christmas break, just leaving the war room to go to the Las Vegas Motor Speedway on track testing days. So things were very intense to get the stack developed and to get things working for race day. So if we flip to the next slide here, this next photo clip is just a short clip of an autonomous warm-up lap with some of the team in the background and also some of the sponsors on the track watching here. So I think this one's pretty short, but you can just kind of see the little live view there. So we can kind of flip to the next thing here. So this is just sort of behind the scenes. This is Sid and Haro. These are the team principals for UCSD, so some of the student team leads. Here I would like to introduce Cake. So also Zihao. He spent his entire Christmas break on site at Las Vegas and took over much of the direction for the perception stack development. He was an absolute rock star on this project, and teaming up with him on site personally for me was a great experience. So he's going to take us through a video that he put together for the perception team software stack development for IAC at CES in Las Vegas. So Cake, you can go ahead and take it away.
Yes, thank you, CK. So go to next slide and let's watch the video. So the main work in this race is to develop the perception stack, and everything before the object tracker is using AutoWare. So I have to take in charge of designing the multi-object tracker. So I first started building with a very fast simulation environment, and then single object tracker and the multi-object tracker, as shown in this video now. And after that, we decided that the bounding box isn't needed, so we ditched bounding box, only track the center of the bounding box. And this is a demo showing the testing of different scenarios. So we want to make sure that the tracker doesn't crash in any circumstances. After that, we decided the code is running fast enough, so worked it in rows and using rollback to test how the tracking works. and tune the parameters in the entire pipeline. And here you can see it's tracking the opponent car. We achieved roughly 40 to 50 meters of detection range. And then we deployed the perception stack on the real car. However, the raw spec recording was kind of corrupted. But when I was looking at the RVS on the car, when it's plugged on the car, it's very smooth. So back to the lidar perception stack on the diagram. So the perception stack consists of it's all using traditional software. In this race, there's another team in UCSD developing car detection based on point RCNN. However, their code didn't win into this race. So it's 3-point clouds transformed into 1-point cloud and then fed into a ground classifier. And we threw away the long ground points. And after that, we filter out all the single points which might interfere with later stages. After we filtered the outliner, we pass the remaining point cloud to the Euclidean clustering load, and it outputs bounding box. But these bounding boxes are very noisy, so we have to track all the different bounding boxes across time. Because sometime it might drop one frame, the car might not be detected, and it might pop up back again in the next frame. So this is what the tracker does. So next slide, please. Oh, I think you are using the earliest. Okay, I'll just describe that. the version isn't completely right. So in the tracker, we normally need to maintain all the different tracks. So under the multi-object tracker, in the background, there is dozens of common filters running together. So for each object detection popped up in the detection range, we have to create a new track and then maintenance the track throughout time. And so this development, you can look at some textbook for the information of how to design the multi-object tracker. But what's different is in reality, when you really start to write the code, you begin to find things which didn't think of. So when I was constructing the framework of the multi-object tracker, I had to reorganize the entire code 2 times just to make it work. The processing order isn't completely as the textbook speaks. So sometimes we might need to reorder the processing because it's a huge number of different moving pieces running together in the code, and you have to make sure that the order is correct. So it's quite hard to wrap the head around, but it was a super cool experience, and I'm very proud of that. So yeah, let's hand the stage back to CK to introduce some of the fun moments in Las Vegas.
Thank you so much, Kik. Okay, so also while our team did not place first, I kind of want to point out that we really came in as the underdogs. Our team was like heavily composed of undergraduates and a few master's students. And we faced down some European teams like TUM and Polymove. They had about like 5 to 10 PhD students and 3 years of European robo race seasons under their stack, and like a mature software stack. So this team was incredibly hardworking, and we definitely have room to grow and develop, and we plan to come back more competitive than ever next season. Yeah. Oh, in one case, 30 grad students. Yeah, some of the teams were intense. So we really did very well. Oh, sorry, Chris, do you want to flip back there? So yeah, all I really wanted to say for this slide is I think that this competition really offers incredible student experiences, lifelong friendships, and just like a really phenomenal opportunity for collaboration. This is just some of like the team bonding events and a hiking trip that Cake took us on where we kind of got lost in a mountain or on a mountain at night. So that was a lot of fun. You can flip to the next slide. So for the student outcomes, this is an incredibly high profile competition in the industry. There's lots of media attention, and they're just really fantastic opportunities for networking. All the students who have come through as graduating team members this year were offered really lucrative offers for elite engineering roles. And this is just a consistent thing that's happened every season. And it's something that we can continue to expect for this type of competition. So you can go to the next slide here. We also just have a short video to close. This is maybe 30 seconds of the winning lap from CES. We'll see the Germany team spin out in the final lap, and then the Polymove team take the win. And then after the clip, I want to hand it off to Chris
accelerating to the outside, 168 through the corners, nearly to 169. Now they crack 169, accelerating onto the front stretch, and a spin from Toom down to the infield and able to continue on. No damage to the car, but what does that mean for Toom? I think that is day done.
Yeah, they will not be able to pass.
So the champions from Indianapolis come up just.
So you saw the spin out there, but what actually happened right after that was all the teams were so excited for the winners. The underdogs in the top pack from the first race had made it through. You saw the spin out, but the other car kept zooming, and they hit the fastest speed that's ever been achieved by an autonomous race car on one of these competitions. So everyone was just going nuts in the pits area as we're like, wow, they did this. Like they had successfully passed like a half dozen times in a row, and they had actually pushed the limits of both the car and the algorithms, and they only spun out once the like absolute performance limits of the car had been exceeded. So it was just a tremendously exciting time, and something you don't see in a lot of other competitions. This is kind of our closing couple of slides here, but we all on the team feel that this is a once in a lifetime opportunity. When you get the chance as a student even to play around with hardware like this, to race a real race car with autonomous software, this hasn't really been done before in the United States, and it's left us with a lot of memories and friendships that we think will last a lifetime. And we're here because we want to grow the team. This is our close. So if you're interested in joining the team, whether that's as a student member, as a sponsor, as an advisor, we want you to reach out to Gary or Alan after this call. We're actively looking to recruit into the perception team that's going to be based out of Berkeley this coming season. And we think it's a tremendous opportunity to be involved from a number of fronts. So thank you for your time, and we'll go to questions now.
Thank you very much, Chris, CK, and Cake, and Gary. I think that we're going to keep the recording going, and if anybody needs to go, we are going to post the recording after the event, and then we will start the QA session. I think Chris and CK and Gary and Cake will be able to continue to stay online and answer our questions. So I will start with a few questions. The number one thing I would like to ask, I'm the person who like to put the car in front of the horse, no pun intended. So for the upcoming event, and then Gary was saying that the rule is always evolving. So what is the most relevant rule that we have to be aware? Is it a single car racing, assuming the track is occupied by itself, or is doing wheel-to-wheel, peer-to-peer competition, or what? So what is the expected outcome for the 2022 season?
So I guess I'll jump in and speculate because they have not published any of that yet. What we saw between round one and round two was going from essentially a time trials format to a relatively simple but pretty well constrained passing. You could only pass in a certain area. The car that was being passed had to maintain a certain position on the track, had to maintain a certain speed. And so all of that gave the attacker, much more bandwidth to program around unexpected events. What I anticipate round 3 will introduce is a relaxation of all those rules. So it will be a head-to-head competition. I don't think it'll be more than 2 vehicles in round 3, but I would anticipate that in round 4. But in round 3, I think it'll be still a speed contest where the cars will trade off to prove which one can do it. But the defender will be pretty much allowed to utilize as much of the track as it wants, and the attacker will be allowed to attack from any place on the track that it wants. So it changes dramatically the vehicle dynamics challenge, as well as the perception challenge and distance of perception. Right now, the cars are all running in the 40 to 50 meter range. And we were using V to V, or actually V to X, X to V, some information that gave us distance to the other vehicle because we had not yet evolved our perception systems deep enough. But I think that will get the accuracy of that, or the distance of that, will begin to be dialed back as they keep raising the bar on the perception side.
Okay, thank you, Gary. I have a quick follow-up question. If it is going to be a wheel-to-wheel two-team competition, there's going to be a challenger and a defender. Now, the chassis are all the same, right? So it's a Formula car. So in terms of the notion of defending, so there are 2 scenarios, right? Number one is that because all the chassis, engines, and wheels and tires are the same, if the defender just keep driving at top speed, then there's no chance for a challenger to pass from behind, right? So if I don't actually, I assume that my system actually doesn't care about my the other vehicle. I just drive as fast as possible. Then the challenger will not be able to pass if my speed is the top speed, even equal speed. Then the challenger cannot pass me. And the second one is that I can drive slowly, but I can drive like the safety car in Formula car, and I'm just driving from left to the right to the left, driving like a drunk person. Then no matter how fast the challenger can go, it also cannot safely pass me. Right. So are there rules to prevent these to turning the race to be trivial?
And again, this is speculation because we haven't seen round 3 rules yet, but those are, I think, the 2 obvious cases that the rules would have to be constrained around. So that's why I said I believe the defender will still have a speed consideration. So it may be capped at, say, 90% of what it's capable of doing, okay, so that the other car has at least an opportunity to do something. Also remember that these vehicles generate a pretty good size aerodynamic wake, and that we have data that shows that we can pick up about 4 or 5 miles an hour coming off of the wake of the vehicle in front of us through a drafting maneuver. Right. None of us have attacked each other from that perspective yet, because that's a little over the horizon. But we do know that that's available. So I think those 2 things will address your first issue. The second one, I'm sure, would be a limitation on the lines of maneuvering off of the race line, and that happens even in real racing. If you can imagine real race car drivers, if they deliberately did a lot of that, they'd probably get black flagged for blocking or for unsportsmanlike conduct or something. So I think we can anticipate there'll be a rule in there that will be we'll have to implement in the methods and the algorithms, and secondarily there'll be race control that'll say, you know what, car 4, that's not the kind of event we're talking about, so bring it on in, you're done for the day. And they've been willing to do that. They acknowledge that they can't write everything into a rule, that at some point the humans have to take over and say, are we getting what we came here to do?
Thank you. I guess that that in that case it shouldn't be called unsportsman behavior. It should be unsports machine behavior.
Very good point.
Another quick follow-up question is that in terms of the race line, are the multiple possible race lines provided as ground truth, including the occupancy grid map that really annotate the track to the team equally, or the calculation of the race line and then the occupancy grid map are the responsibility of individual teams?
The latter. In fact, all they really do is take us to the track and say, here, have at it. So we had to map the track, geolocate the track against Google, because while Google's fairly accurate, it's not accurate enough for what we want to do. So we had to translate that to our simulations. And then we had to develop our own race lines. And the race lines, of course, when you get to the vehicle dynamics of a race car, as you know well, we go into the nonlinear range on the tire and lateral load capabilities. So all of those things are really left to the team to decide how safe and how close they want to operate to the limits at any single cycle, and of course over the entire race line and race lap for them.
Okay, so I will ask one last question on behalf of the Berkeley students, and then I will turn it over to see if any other students have their own individual questions. So there is one question I think related, I'm going to bundle several together, is that to focusing on the perception in order to, to produce the outcome for perception and then output it to the control system, this system, I assume that is fully on board, right? So there's no communication required to communicate with the base station. The base station is trying to only to resolve some exception or startup and then the pit lane controls and then also to command. The perception is fully embedded on the vehicle, and then for students to to develop the perception system, what kind of development environment are they expected to work on? Is it going to be Python or C++? If it's on board on the Ubuntu 20.
So I'll jump in, and Kate may have some additional thoughts here. Yes, the rules require that the vehicles, after they leave the pit box, so in that picture when you saw the car leaving pits, the teams are by definition not allowed to communicate with that vehicle unless it is to give it a speed because it's allowed to in one of the rounds of the competition, or that it's that the vehicle telemetry that's coming back. And if you go back to some of those pictures, you'll remember some very colorful sets of three large monitors that were essentially running real-time telemetry back to us. And if we saw something in there that made us feel like the vehicle was not operating and could be unsafe either for itself or the other vehicle, then we did have essentially an override that allowed us to bring the vehicle back to control. As it relates to programming environment, there is no restrictions on languages or software. We could have written this in theory in Windows 10 and Fortran, but we definitely went the way of open source. So that's why we went with Ubuntu, went with ROS2, went with what we could from AutoWare, and then tried to do the least amount of work that we could do. The Python C++ question is, in my estimation, really only a performance question. If the method and algorithm can meet the requirements, then it certainly can be written in whatever language is the best language for that particular requirements, or maybe the best language for that team because they happen to have more experience at that. We tended to go, a lot of code tended to end up in C++. And I think that's just because a number of the programmers on the team, and particularly industry, tends to go that direction. But that doesn't mean that that's a requirement by any stretch.
Okay, I see that CK and Chris also pitching in the chat box.
Good.
CK and Chris, do you guys want to elaborate on the coding part? I think that is the prerequisite a lot of students will be interested to know.
I think the prerequisite is really going to be like getting familiar with like ROS2. A lot, like we mainly use ROS2 nodes for like the majority of the development. C++ is, I mean, obviously, like it's not, it's compiled versus like a real-time language. So it's slightly preferred to Python, but a lot of the stack is in Python. ROS is cross-compatible with both. You can learn to like write ROS nodes using Python and with C++. So like say you're somebody who's very familiar with Python, but like C is not your strong suit. You are still able to like develop very well within using Python within ROS, which is what our team actually primarily did, because that was the majority of us were more familiar with Python versus C++. So.
Okay, Among asked a question about the ROS1 and ROS2, and I think Chris has already replied. Among, do you have any follow-up questions or? Yeah, so we are monitoring the questions both on the chat box and online. Okay, so are there any other questions? Anybody would like to turn on your microphone and ask questions for CK, Chris, Cake, and Gary? Okay, if there's no question, let me also ask another question. I think that the one challenge is that a lot of top teams, they have years of experience and a lot of senior graduate students. So that's highlighted by Gary. But also one thing that Gary also mentioned is that this race encourage open source development. So Gary, have you seen any teams open source any part of their solutions? Of course, no team will open source their entire deck, but are there any other, community building and solution sharing, kind of movements that really, adhere to the open source notion from other more experienced teams?
Yeah, I think the primary example of that is Tomb, after winning the Indianapolis event, posted up a big chunk of their stack, including their MPC control system, which works on a tube MPC, which is very state of the art. So a lot of those, and I believe the Euro race also has put up a good chunk of their stack, made it available to everybody else. It's what we've seen is that if one of the teams has a question about, how are you doing this or that, it's been very comfortable to go and talk to the other teams, and often they will refer you to 2 or 3 papers, either that they wrote or one of their students wrote, or that they used for their core method or core algorithm and that kind of stuff. So there's the teams have been all, I think, very collaborative from that perspective. But at the same time, it's a competition. So yeah, we don't get everything. And at the end of the day, it really is how well do you test, how well do you make your stack work at the end of the day. I think, very quickly we're going to arrive at a point where the Euro teams are at a point of diminishing returns. I don't think they can get much better, but we still can. So that's why I think we really want to put our heads down and prepare for next fall's event, and really come to the fight with a good solid level 1 autonomous vehicle racing stack.
Okay, so here will be probably my last question for today. And I know that Gary, you would like to organize a follow-up technical discussion meeting to really sort out what needs to be, what needs to be done in terms of the engineering-wise. So those are not suitable for a seminar like today. So I think we're going to follow up and see, who will be the Berkeley students who are interested to participate. And then my question is access to the platform. The ROR system at Berkeley, actually, we are fairly familiar with the color. In fact, we actually use the lidar, a 3D scanning system. We actually scan a Berkeley major map that span the Berkeley downtown all the way to Lawrence Berkeley lab, and then to the hillside. And we are happy to share the video with anyone interested. We are fairly familiar with the color, but again, putting the car in front of the horse, I think that for your team, your goal, the next immediate goal is in May, right? So the EV Grand Prix. So the EV Grand Prix is a go-car and then has the sensor suite installed on the car. For Berkeley team, how is it possible for us to get access to that? Because the EV Grand Prix, no matter how simulation performs, is still different.
So this is a really easy one. So as when Chris moved to Berkeley, one of the things that we realized was that for the perception team there would need some tools to work with. So we built out a sensor frame that includes lidars, cameras. It didn't include radar because we were at that point not necessarily focused on using the radars. It includes a computer, ROS2 computer. And so therefore we tried to build a platform and they installed that on a little roll around card that they could use to actually test the real software. So that I think, and we're certainly committed to continuing to upgrade that particular system. So there's a platform, a real hardware platform that people can go and work with and test their code and check out what they've got.
So if Berkeley wants to get a sync for the same EV go-car platform, for most of the people in Berkeley, actually, you may not know that we actually have satellite campuses. One is in Richmond Field Station, and Berkeley recently signed a contract with the NASA Ames Lab in Mountain View. So we are also going to build a satellite campus over there. For Richmond and the Ames Lab in Mountain View, we actually have racetracks. We actually have, I wouldn't say racetracks. I should say the tracks that can be raced on the road. So I think that Gary, so if we want to have a go-kart, what's the cost? What is the cost for that platform?
So I would say for the basic go-kart, it's around $7,000 to $9,000, depending on sparing levels and a few other things that you want to do. The sensor package that we're using on the go-kart probably has an equivalent cost. So I think that what we're generally looking at sub $20,000. For a built up, and we have a lot of the mechanical design done, actuator design done, low level controller designs done between us and UC San Diego, and I know I can speak for Jack. We're more than happy to share that as a starting point if you guys want to go off another direction, or just let you use it.
Yeah. So CK and Chris, I think for the purpose of next meeting, I think we may be able to invite everybody to the Richmond Field Station to our workshop, and then we can have a meeting with Gary from there. So and CK and Chris can have assessment about whether we can build a junior test track over there. To more mimic the same configuration that is one step above the simulation. But Gary, if you want to work on color, I think we will have students who are very experienced on that. But of course, for other other driveware simulators, probably you guys are way ahead of us because at least in our group we have been focusing on color in the past. Yeah. I see there's a question. Oh, yeah, Gary.
So yeah, I saw a question on on essentially the dynamics or controls model. Yes, we have typically for the first round or two, we did use a bicycle model and basically used a modified version of Pure Pursuit because they're very simple to implement and very rugged and reliable if tuned well for the speeds. What we're working on for Gen 2 is a more rugged 4-wheel MPC that is actually the data for that is coming from a professional race car package that's providing us the dynamics and control laws that we need to actually utilize that. So that's part of what our roadmap for next October looks like.
Great. Thank you, Gary. I think that's all the questions I have and all the questions I have seen from the chat box. At this point, do we have more questions?
One last question I got from Eddie here is, it didn't sound like you were using any kind of reinforcement learning or anything. We were wondering what if there would be any benefit to trying that approach in the future.
Yes, we've certainly in the path area, utilizing the tube MPCs, we feel like there's some reinforcement learning opportunities there. Clearly, as I mentioned, and it's somewhat obvious, it's hard to get a lot of data from the race car just because it just doesn't get that much track time. And the reinforcement learning that we've looked at probably requires more data than we've been able to assemble to date. But we do talk about that on occasion, and if somebody had that as their cause and wanted to really work on that, then there definitely would be some support for how to fit that into the model.
Thank you, Gary. I guess we are actually more getting into the detail of the technical challenges, and I think that that's not a suitable venue to dive any further deeper in this seminar. Yes, as I said, I will communicate with the CK, Chris, and Gary, and we'll try to organize Berkeley students to tour our facilities in the Richmond Field Station, and also get a meeting with Gary to really outline what will be the next action items from Berkeley, what we can do. So yeah, so if you want to participate, you can contact Gary and myself, and then we will put out what will be the next get-together meetings to focusing on discussing or technical aspect of the Indy Autonomous Challenge. Okay. Do we have any other questions? One last chance. All right. So if not, my deep appreciation and thank you for Gary, and a big round of applause for CK to really organize this. And I think that CK has been very detail oriented, and most people don't know that CK actually wrote endless amount of email coordination, and also the first draft of the summary of this meeting. And then when I look at the email, and I was so surprised, probably it's the most detailed talk summary that I've ever seen in Berkeley. It's like a whole page of the discussion details. Yeah, so it's a very thorough organization by CK. And Chris and Kate to give us a high level overview of the challenges and also stir our students' interest. All right, Gary, so looking forward to our next meeting. Thank you so much. And thank you everyone for coming. And then we're going to post this video online on the Vive Center soon. Thank you.
Thank you, Dr. Yang. Appreciate your help.